Hello everyone, welcome back to my YouTube channel. My name is Ved Prakash, and in this video we will talk about different distance metrics in machine learning. Understanding distances are crucial in developing machine learning models. Some of supervised machine learning model and unsupervised machine learning algorithms are dependent on distances, just like Euclidean distance, Manhattan distance such as k-means clustering and k-nearest neighbors. Euclidean distance is the most commonly used distance metric, and it measures the straight line distance between two points in a multidimensional space. It is simple to calculate and intuitive to interpret, and making it a popular choice for many applications. It corresponds to L2 norm of a difference between vectors and vector spaces. The cosine similarity is proportional to the dot product of two vectors and inversely proportional to the product of their magnitudes. So the Euclidean distance between A and B will be D. Formula for Euclidean distance can be given by D is equal to P1 minus Q1 का whole square plus P2 minus Q2 का whole square, and formula for Euclidean distance can be given by under root of P1 minus Q1 का whole square plus P2 minus Q2 का whole square. And we use this formula when we are dealing with two dimensions. We can generalize this for n dimensional space as dE is equal to sigma I is equal to n and pi minus qi का whole square and square root of that expression, where n is number of dimensions and pi and qi are data points. Most machine learning algorithms, including k-means, use this distance metric to measure the similarity between observations. Let's say we have 2 points as we have shown above, and like the next one is Manhattan distance. Manhattan distance is useful when the dimensions in the data have different units of measurement, while Chebyshev distance is ideal for applications where the maximum difference between two dimensions is more important than the individual differences. Manhattan distance is also called L1 distance. Sum of differences between coordinates across all the dimensions represents Manhattan distance. For example, we have two data points in a 2D plane, A P1, Q1 and B P2, Q2. So this is the distance formula for Manhattan distance. D is equal to mod of P1 minus P2 plus mod of Q1 minus Q2. For example, consider two points A 2, 3 and B 5, 7 in a two-dimensional grid. The Manhattan distance between them will be mod of 5 minus 2 plus mod of 7 minus 3, that will be 7. Now the next one comes Chebyshev distance. Chebyshev distance is similar to Manhattan distance, used to find the distance between two grid points in a grid system. But there is one difference between this and Manhattan distance. It moves diagonally as well as horizontally and vertical direction. It moves diagonally as well as horizontal and vertical directions. In this figure, Chebyshev distance between A and B can be represented as D is equal to max of mod of P1 minus Q1, P2 and Q2. In addition to these standard distance metrics, there are also specialized distance metrics such as Mahalanobis distance, which takes into account the covariance between variables. This is especially useful in applications where the dimensions are correlated. Mahalanobis distance is a measure between a sample point and a distribution. Mahalanobis distance from a vector y to a distribution with mean mu and covariance sigma is called D is equal to Mahal y comma x, and it can be given as D is equal to square root of y minus mu and sigma minus 1 into y minus mu. This distance represents how far y is from the mean in the number of standard deviations. Mahal returns the squared Mahalanobis distance d square from an observation in y to the reference samples in x. The Mahal function mu and sigma are the sample mean and covariance for the reference samples respectively. But that's not all. There are also other important distances metrics used in machine learning, such as Hamming distance, which is used to measure difference between two strings of equal length. The Haversian distance is used to calculate the distance between 2 points on a sphere, and cosine distance is measure of similarity between two non-zero vectors of an inner product space. The Haversian formula calculates the shortest distance between 2 points on a sphere using their latitudes and longitudes measured along the surface. It is important to use in navigation. The Haversian can be expressed in trigonometric function as Haversian is equal to sine square theta by 2. The Haversian of a central angle, which is d by r, is calculated by this fall. The Haversian of the central angle, which is d by r, can be calculated as Haversian phi 2 minus phi 1 plus cos phi 1 cos phi 2 Haversian lambda 2 minus lambda 1, where r is the radius of the earth 6371 km and d is the distance between 2 points. Phi 1 and phi 2 is the latitude of the 2 points and lambda 1 and lambda 2 is the longitude of the 2 points respectively. Solving d by inverse applying the inverse Haversian or by using the inverse sine function, we get d is equal to RHAB inverse of h equal to 2r sine inverse under root h. Understanding or we can say it 2r sine inverse underscore sine square phi 2 minus phi 1 by 2 plus cos phi 1 cos phi 2 sine square lambda 2 minus lambda 1 by 2. Understanding the strength and weakness of each distance matrix is crucial in selecting appropriate matrix for a given problem. By choosing the right distance matrix, we can improve the accuracy and efficiency of our machine learning model. So whether you are a beginner or an experienced practitioner, taking the time to learn about these distances will undoubtedly improve your models. By understanding the various distance matrices available and their applications, we can select the most appropriate distance matrix for our specific problem and improve the accuracy of our model. In case you have enjoyed this video, please do not forget to subscribe and like the video. You can also comment in case you have any doubt. Thank you for watching.